When light falls on the surface, a part of it is reflected, a part of it is scattered, and a part of it is absorbed. And today we will study about the scattering of light. So when light falls on any particle or any surface, a part of the light gets scattered in all directions, and we will learn more in detail about the scattering of light. To study scattering of light, we need to know the nature of light. In the earlier chapter, in the earlier slide or earlier lesson, we have learned that white light, when it is passed through a prism, it splits into these 7 components. And why does it split into 7 components? Because in air, all the components have the same speed. And because they have the same speed, they travel together and light appears white. But when light enters glass, the components now have different speeds. And because they have different speeds, they bend to different extents, and the light is split into its 7 colors. Now, if the components have different speed, then who has the largest speed? And we see that the red light has the greatest speed or travels the fastest, while the blue light, or the violet light in this case, has the least speed. And the reason is because we look up in this picture, here you see the red light has got the largest wavelength, while the blue light, the wavelength is much less. So the wavelength of red light is large, while that of the violet light or the blue light is less. Hence, red travels much faster than violet. In fact, when we compare the speeds, the wavelength, we see that the wavelength of red is 1.8 times that of the blue. And because of this difference in speed, this uneven scattering that takes place, we have different phenomena, like why the sky is blue, the sun is red during the sunset. This we will see in the next slides. So here we have seen what is scattering of light, that when light falls on a particle or it falls on a surface, it gets scattered. We also have seen that there are 7 colors, and the 7 colors, when in glass, it travels at different speeds, and the wavelength is not the same. The 7 colors, the wavelength is not the same. The red has a greater speed with a greater wavelength, and the violet has the least speed with the smaller wavelength. Here we'll see the type of scattering. The scattering is of 2 kinds. The way a particle or surface scatters light is of 2 kinds. It's called the even scattering and the uneven scattering. Now, if the particle scattering light is greater than the wavelength of light, you get even scattering. In this case, all the 7 colors are scattered equally. Here the particle size is greater than the wavelength of light. Then even scattering takes place, which means all the components are scattered equally. Here you get the light is incident, and when the scattering takes place, all are scattered equally. We have the red that is scattered, then the blue, the green. These are some of the components I have given you, and there is all equal scattering. But if the size of the particle is less than the wavelength is larger. Then there is uneven scattering taking place. The particle size is less than wavelength of light. Then there is uneven. Now in uneven scattering, here you have white light that is incident, and in uneven scattering it's the blue light that gets scattered most, while the other components are scattered, not scattered as much. It's blue get the shorter wavelength. It being the shorter, blue being of the shorter wavelength, gets scattered most. So there is uneven scattering take place and blue is scattered most. So again, to repeat this, we have type of scattering. The type of scattering depends on the size of the particle. Even scattering will take place if the particle size is larger than wavelength. Uneven scattering will take place if particle size is less than the wavelength of light. And in uneven scattering, it's the blue light that gets scattered more. Now let's see why the sky is blue. First, the atmosphere is made up of small particles, and the size of these particles are less than the wavelength of light. So if the size of the particle is less than the wavelength of light, you will expect uneven scattering to take place. What do you mean by uneven scattering? It is the blue light that will be scattered most. So when light falls on these particles, from the sun, you have this, it is the blue light that gets scattered the most. And because the blue light gets scattered the most, the entire sky looks blue. So to go over it again, you had the blue light, you had the sunlight falling on these air molecules or on these particles which are very small, and because of which it was the blue light that got scattered the most. The red light did not get scattered as much, and hence the sky appears blue. So to go over it again, the atmosphere is made up of small particles, that is important, and because, and how small? Less than the wavelength of light, and hence uneven scattering takes place and blue light gets scattered the most, making the sky blue. The next question, what would be the color of the sky in the absence of atmosphere? So if there is no atmosphere, means no particles. No particles means no scattering. No scattering means a dark sky. The sky would appear black and dark because there would be no scattering of light. That's what happens in space. In space, the sky appears dark because there are no particles to scatter light. You need to remember that there is more sunlight in space than in the atmosphere, but the space appears dark because there are no particles to scatter light. So here we learn why the sky is blue. The sky is blue because the particles are very small, smaller than the wavelength of light, and the blue light gets scattered more than the red light. And that's the reason why if there's no atmosphere, there would be no particles, no scattering, the sky would appear dark. And that's what happens in space. In space, the sky is dark because there are no particles to scatter light. Next, why are danger signals red? And that's because of uneven scattering. So when light falls on a particle, if the particle size is small, we find that there is scattering. But when there is scattering, the blue light gets scattered maximum, the green light gets scattered a little less. However, it is the red light that scatters the least. So it travels the largest and the longest distance. So danger signals are red, so they can be seen from a very far point. Like if you take this point now, if there's a person standing here, he will not be able to see the blue light because the blue light is already scattered. It is only the red light that will reach him and will enter his eye. So red light travels the most. It can be seen from a very far point. Hence the danger signals are red. So the points are here. First, you got to write the red light has the longest wavelength, and hence it is scattered the least. Here the scattering is done by air molecules, by fog, or by smoke, or other dust particles present in the air. And for all these particles, the particle size is less than the wavelength of light. You need to mention this point. So the red light is scattered the least, and hence it travels the farthest. And because it travels the farthest, it can be seen at a distance. So that is why danger signals are red in color. Why is the sun red in color at sunrise and sunset? To understand this, let us see the difference in the positions of the sun during noon and during sunrise and sunset. During noon, the sun is overhead, and the sunlight which travels down has to pass a very small distance through the atmosphere. But when the sun is at the horizon, now the sun light travels a larger distance through the atmosphere, much larger. And because of this, it's only the red light that reaches our eyes. The blue light gets scattered, while it's only the red light, because it travels the fastest and travels the furthest, it reaches our eyes, and hence for us the sun appears red in color. It's important to note, for a person at this position here, the sky will appear blue, but for a person here where the sun is setting, the sky will appear, or the sun will appear red. So here we go over it again. At sunset, sunlight travels a larger distance through the atmosphere. Then the particles in the atmosphere scatter blue light the most. Hence, blue light does not reach the observer. It's the red light that is scattered the least and travels a larger distance, and it's a red light that reaches the eye of the observer. Hence, for the observer, the sun appears red in color. Like here you can see, it is the blue light gets scattered even before it reaches the observer. It's only the red light that reaches the observer. However, during the noon, the distance traveled by the light is very less through the atmosphere. Hence, all the 7 colors reach the observer. Well, now let's go through this activity which is given in your textbook on page 196. And this explains why the color of sun at sunrise and sunset is red. So in this experiment, first place a strong source S of white light at the focus of a converging lens. So here we have a source S that is placed in front of a converging lens. A converging lens is a convex lens. So this is a convex lens. And at the focus of the lens, you place a point source. So the light that comes out from the point source will get refracted and will go parallel, and that's how we get a parallel beam of light. And in the next part, allow the light to pass through the transparent glass tank containing clear water. Allow the beam of light to pass through a circular hole made in a cardboard. And that's here. Here we have a cardboard. And there is a circular hole made in the cardboard. And the light now passes through this circular hole. Of course, it doesn't pass through this part because it is opaque. It will only pass through the circular hole. Then obtain a sharp image of the circular hole on the screen using a second converging lens as shown in the figure. So here is another converging lens, another convex lens, and these rays that are parallel. After refraction, you know they will converge at a point and you get a bright spot on the screen. Now in the next part, now in the same, we are going to take 200 grams of sodium thiosulfate in this clean water. So you take sodium thiosulfate, you add it to this water, and then add 1 to 2 ml of concentrated sulfuric acid to the water. So you take sodium thiosulfate and to that you add sulfuric acid. Now both will react and they'll give you sulfur, colloidal sulfur. Small particles of sulfur will appear in this beaker because the reaction between sodium thiosulfate and sulfuric acid. Now we do the same thing. We keep a point source. From the point source at the focus, and the light now comes out from the focus, and when it passes through a converging mirror, lens, that's a convex lens. That's a property of the convex lens, it goes parallel. Now as this light goes parallel and it hits this bits of sulfur, I'll just put them in black now. Sulfur is yellow, but I'll put them now in black. Maybe I'll put them in another yellow. So this light, the white light is scattered by these sulfur, colloidal sulfur. And here uneven scattering will take place because this particle size is very small. So the blue light will get scattered out in this region. These particles will scatter blue light. Hence, when you look at this solution after some time, it will all appear absolutely blue because the colloidal particles are scattering the blue light. However, the red light will remain unscattered, and the red light will then travel further up because it is unscattered. It will converge here, and at this point now will appear with red in color. Earlier it appeared white in color, now it will appear red in color because the blue light has already been scattered. So if you watch this beaker from very close, if you watch the beaker from here, if you have your eye here and you watch your beaker from here, it will appear blue, but this spot here will appear red. Here this spot will appear red because it's a red light that travels the longest, the furthest. So we just read the text. You will find microscopic sulfur particles precipitating in about 2 or 3 minutes. As the sulfur particles begin to form, you can observe the blue light from the 3 sides of the glass tank. This is due to the scattering of short wavelength by the minute colloidal sulfur particles. Observe the color of the transmitted light from the 4th side of the glass tank facing the circular hole. It is interesting to observe at first orange or red color and then a bright crimson red color on the screen. And this clearly shows that Blue light is scattered more and travels the least, while the red light is scattered the least and travels the most. Next, why are clouds white? Now we see that clouds, they're made up of very large particles of water. And because they're made up of very large particles of water, the light that falls on them undergoes even scattering. All the particles are scattered evenly. And since this even scattering takes place, they appear white in color. So if you were to write why clouds are white, first you will write clouds are made up of large particles. How large? Larger than the wavelength of light. And because they're made up of particles larger than the wavelength of light, there is even scattering taking place. All the components, all colors are scattered evenly. And because all colors are scattered evenly, they appear white in color. So we have clouds are made up of large particles. How large? Larger than the wavelength of light, and hence even scattering takes place. All colors are scattered evenly, and hence clouds appear white in color. But however, the sky around appears all blue in color, and that's because in the sky, in the atmosphere, we have these small particles. Smaller particles, and these smaller particles carry on uneven scattering. They scatter the blue light more than the red light, and hence the sky appears blue while the clouds appear white. Here there is even scattering, all colors scattered, and here there is uneven scattering. The scattering of light has got another name. It's called the Tyndall Effect. So Tyndall Effect is nothing but scattering of light. It can be clearly seen in a forest. Here in the forest you see the light that has been scattered, and the particles that scatter light are these drops of water given out by the plants during the process of transpiration. These drops of water, they scatter the light, and hence we can see these beams of light coming into the forest. So when sunlight passes through a canopy of a dense forest, there are these tiny water droplets in the mist that scatter the light. So we can see Tyndall effect in a forest. The same phenomena can be seen in a dark room. In a dark room we have particles of dust in the air, and when light is allowed to enter the dark room, as it enters, it is scattered by these particles, and hence the path of light is visible. All these particles will scatter the light, and here the path of light is visible. So this is a Tyndall effect taking place in the dark room. Therefore, in this region you will see the light, because they're all scattered by, the light is scattered by these dust particles.